Okay, so welcome everybody. If you attended our first session this morning, so you know who I am. My name is Guillermo, for those who are just attending this workshop on Python programming. The idea here is this mini workshop is completely separate from the introduction to HPC. So I will introduce a few things that will overlap a little bit with what I showed this morning, but I cannot assume that you attend this morning. So there will be a little bit of repetition. But I will go fast on that because everything that we will be doing today will be from the web interface, from Open on Demand. So it will be much user-friendly, if you like. So this is the idea. Today and Friday afternoons, we will be covering a little bit of Python programming, short programs. I will not dig too much into large programming structures or complex developments. This is meant to be a very introductory course. And also I try to make it as visual and enjoyable as possible, so you have an appreciation of the beauty of the language and the particularities of this programming language. And then we have a lot of material, so we need to cover all that. So what I will be doing is focusing more on the examples, and you can read on your own today, tomorrow, and Friday. You can pick up the material on your own. So the focus here is to understand the examples. It's a little bit guide you through driving into the language. And that's how you actually learn a programming language. You don't learn by following a reference with all the possibilities for variables, for all the functions, internal functions, methods, classes, all that in a dry way. You don't learn that way. Yeah, you can use that as a reference when you know how to program, but at some point it's pointless to try to do that. So you can follow material. What I will be doing is pretty much everything on Open on Demand. So I will jump directly on how you access Open on Demand. So this is what we are going to do. And I will probably do that again. So this is the idea. In my case, I will skip the duo. But this is what we are going to do. I will copy for you the link because everything will happen on a web interface. And so open your browser, go to this website, and you will be asked for your username, your password, duo credentials. And after you do that, you will land on a page like this. Let me see, we are still. So the idea is that you reach this first page. Now, the materials that we will be using, let me see if I can go here to them. So, by the way, I have here pretty much, let me see. Okay, I probably have. Probably need to correct something. But everything will be on a Jupyter Notebook, so you can follow that from there. And that's what will be doing. Okay, so what I'm doing here is click on clusters and going to Thorny-Flat shell access. And now I will be going to my Scratch, and I will be copying this. So the command that you need to do, that you need to execute is this. Let me type it here. most likely it's better if you go to your Scratch. And I will create a Jupyter folder here. And here you will execute this command. And I will copy that for you. Okay, so I will be copying this command here. Just copy the line, the complete line, not just the link, the complete line. And you go and open your terminal here. And the reason why I'm using my Scratch and not my home folder is because I am really short on a space on my home folder. So maybe it is not enough for all the materials. Or it's not that bad. Okay, probably I can do it here and it will be easier for everybody. Okay, so I can clone the repository directly on my home folder. That's the first step. You go into Open on Demand for Flat. You open your terminal here. Let's see if I can sharing this. It's better if I share this. There. Yeah. Let me see. Maybe I can do this. Yes. So you go here, clusters, Flat shell access. That this will open this terminal here on the web browser. Everything will be inside the web browser. And from there, you execute this command. Right? Now, what I will be doing now is to create an interactive session. This is new on the cluster. So you click here, or you click in interactive apps, it's the same thing. And you click here in Jupyter Notebook. Now, I will try to use this one. I think this is okay. I will select here environment module. So there are several ways of accessing software in an HPC cluster. Modules, singularity containers, on the environments. We will explain that, and you don't need to know that. You can just pass that as a black box. Just follow the instructions. The important thing is you select this one. You select maybe the latest version here. And Jupyter Lab. I will not be using a GPU, so you select standby. Let's say 2 hours. That's what we have for today. A CPU cores, that's okay. No GPUs. So you put 0 here. And you just click here. Now, what is happening is you will be receiving a compute node, one of the compute nodes in the cluster, where you will be able to run, execute, and you have 8 cores, in my case, 8 cores, dedicated for the execution of the code. I don't really need 8 cores, but it's more than enough for what I will be doing. And I asked for a couple of hours. So on a standby, if you select a standby, you can ask up to 4 hours of execution. So that's, let me see, okay. Okay, now you see something like this. If you are following this, and I will lower a little bit the pace on this, so you have some time to reach this point. You will see a button like this, connect to Jupyter. You click there, and you will get another tab on your browser, and you will see the icon for the Jupyter Notebook. And let me see. And after you execute this command right here, this cloning of the repository, you will see this folder on your personal home folder. You click there, you click in Python, and now we will be concentrated for the entire session of today to the basic language, the Python language. You click there, and let me see if I can stretch this a little bit because it will be short. I didn't understood that your question. How do I run the Jupyter Notebook command? Well, let me refresh what I did. First, I went here. You see, open on demand, like something like this. Something like this, just this. So I will copy and paste in that again. Here. So this is just click there, and you will be entering your username, password, duo, and you will be in something like this. So that's the first step. Step number one, reach this point where you see this logo, you see the message, you land there. Now, second step is clicking here and clicking in Jupyter Notebook here. This the left bar, you will see Jupyter Notebook. You click there, and you see a form for opening a Jupyter Notebook. You select environment module. You select the latest version. That's okay. You select here standby. You select here Jupyter Lab. 2 or 4 hours, doesn't matter. No more than 4 hours. It will not accept more than 4 hours, but 2 or 4 hours is okay. 4 or 8 CPU cores is okay. No GPUs, otherwise it will fail because standby will not offer GPUs for execution. And at the end, you click here in launch. Tell me if someone is not able to reach this point, I will go and do it again, and no problem at all. And you should be able to see at some point, after a few seconds, half a minute or something, you will see a tab like this with a button here. It says connect to Jupyter. You click there, and you end up opening a window like this, and from there you access the notebook that you want. And for the notebook, as we did it here, I execute this command. I open a new on the terminal that I create, clicking here, shell access. It will open something like this. I execute this command, so it will download all the materials. I will copy and paste this. and you will see it will download the files. Uh, not that big, it's relatively small, but all that. And you will be having a folder here. Here, where you click, and after you click in Python, and after you click in chapter 1. And you see something like this. After a few seconds, it will refresh and you will see something like this. Tell me, we have 19 people. Tell me if any of you is not in this notebook. It should be, this is crucial. You need to reach this point, otherwise it's like watching television. So you will not able to interact, to do anything. So the idea is for you to reach this point. And there is a lot of material here, so I will not have time to cover all the material. So I will be jumping basically from the examples one by one, concentrating in what you can learn from them and where you can learn from them, from the rest of the material, from the narrative in the notebook. But I don't have time to go and review all this. So let's, okay, tell me if, got it? Okay, so you have it, Kylie, you have it. Tell me if any of you is not in the Jupyter notebook right now. Let me see. I probably can pick a little bit how many jobs are running here. So I see a number of you running the Jupyter. Okay, that's good. So yeah, so many of you are running. So please tell me if you are not in this list. I don't know how many you are. Yeah. That is not running the notebook. Everyone else is doing it. So I'll find the notebook inside the okay, let me. This is the idea. Let me see here. Did you execute this command? That is also in the chat. That's first thing. Now, okay, that is one possibility. If you have a quota that has been exceeded, some of my colleagues will try to help you, try to free a little bit of space, or what you can do is to execute this command, not on your home folder, but moving into the Scratch, or like this, going to the Scratch. And now here you execute the command. Here you can execute the command. So let me see. So here you can execute the command. That is, it's not that big, but it's still, it's 174 megabytes. So if you are really, really close to filling your quota, yes, it may be crosses the limit. Okay, that's another option. If you want to run it on your own computer, it's okay. No problem with that. In fact, we don't need a supercomputer for running the kind of things that we will be running today. So it's perfectly fine, and any computer can do that without an issue. Now, here, when you open here you will see in your folders, I have many stuff here, but you will be able to see a folder called notebooks underscore for SIAH. And you click there and you will be able to see more folders. There is one called Python, and inside that Python subfolder, there is one called chapter 1 language syntax. I hope all of you are in this place, in this location, and we can start looking into the notebook. Okay. This is the idea. Python is a easy to learn, still powerful programming language that is widely used in scientific computing. Some other languages could be, for example, R, which is kind of similar, more oriented toward statistics. Julia is a newer language, not so popular compared to Python or R, but still, those are what I call the triad of high-level languages. And of course, there are some other languages in the low-level world, like in the low-level languages, closer to the machine, like Fortran, which is a very old language, but is still widely used in scientific computing, C, C++, sometimes Java, in the private sector, let's say, MATLAB, Mathematica. There are many languages for scientific computing. But Python is one of the most popular languages. And this is the language that we will be demonstrating today. We will be working with it. Now, in these Jupyter notebooks, or the Jupyter notebooks are a very easy way to start learning the language, executing code without having to write big programs to allow you to experiment, to try, to change. So this is one way of working with Python in an interactive scientific computing. The idea here is that you type in those boxes code, and you execute that code with clicking, in my case, the button Shift and Enter. When I execute that, I am executing that particular box, and I can go one by one executing all the boxes. We don't have time for that, but just to tell you that you can execute on a Jupyter notebook. Each code box can be executed independently. Or in this case, I can execute the entire code by clicking here in, let me see, here, when you see those couple of triangles, you click there and you can refresh the Python kernel and execute the whole notebook. It takes a few seconds to do that. And what we will be doing is reviewing the different parts of the language, focus on the examples. So let's go into that. So I thought Python is multi-platform, so you can use Python on a Windows machine, on a Mac, on Linux, any Unix system. Is a high-level programming language. That means that certain things are very relaxed compared with other languages. So you don't need to declare for a variable of which kind of variable it is. If it's a number, it's a real number, or it's of that is a word, or like a string of characters, and you can change that on the fly. So there are a lot of facilities or niceties of this language. we pay a price for that somehow, so it's not the most performant language. But if you work properly, you can get the best of Python and still be able to delegate some critical functions that are computationally expensive in some other languages and try to get the best of both worlds by efficiently combining languages on this. So that's the main message here. You see the current version of Python is the 3.12. As you saw here, the version that I am running is relatively recent version. It's right here on the watermark. So I'm running on a 3.11, which is the newest, is the latest version that we have on Thornflat. But for the purpose of this notebook, any version, I think, from 3.8 and beyond, or newer, it's okay. You can run the entire notebook with 3.8, 3.9, 3.10, 3.11. It's okay. So now there are some particularities of the language. I will allow you to read that later. I will try to keep. I would like to keep a little bit the perspective on the advantages or disadvantages of the language. One of the advantages is the easiest is that it's easy to program. You develop code really quickly, which is very, very nice feature when you are dealing with scientific code. Everything is half broken, half right, half wrong. So you need something that can be executed and can be developed quickly, and where you can introduce change on the fly, because things are not so clear. That's the whole purpose of research. Things are not so clear from. It's part of the learning process. It encourages some good-looking code to a certain point. Is well documented. They have a lot of libraries for many things. So as this is attached somehow a little bit with machine learning, with deep learning, many of those deep learning, artificial intelligence frameworks for what I call classical machine learning or deep learning, they have packages linking to via Python. So that's another advantage. There are many, many packages for statistics, for graphics, for image processing, and so on. It's very rich, which is another good thing. You don't need to reinvent the wheel. There is probably a library somewhere that do something closer to what do you want, and you can start from there and customize the functionality to your interest, to your needs. However, there are also some disadvantage to this language. It's not as fast as, for example, C, Fortran. On the balance, for some of those numerical intensive operations, you can work or you can rely on other packages like NumPy. We will be touching a little bit of NumPy or Pandas or some other packages that were written in Fortran or C, and they are very, very efficient on the numerical side. And at that moment, you take the efficiency of those languages or those libraries that are underneath NumPy, for example, and still program at very high level with the advantages of Python. So that is another thing. The current version of Python is the version 3. There is a difference between Python 3 and the old version Python 2, which is pre-COVID, let's say. So that has been deprecated since 2020. So probably nobody is programming or has code, except if you are really, really unfortunate and you receive Python 2 code from your PI, and you have to deal with it. But in most use cases. You are working in Python 3, you don't have to worry about the difference with Python 2. And that's all that you need. So you select one of the Python 3 versions that we have on the cluster, and you are okay. Now, another element here is to understand that what we are optimizing when you say that is not as the Python is not as performant as other languages. But what we mean by that, if you just think on the computational time of a certain execution, you can compare, for example, code written in Python that could take like 1 minute or let's say 10 minutes. But if you write a code in Fortran, you can get that in 10 seconds. Yes, it probably is far more efficient to write certain kinds of codes in Fortran C. But if you combine the amount of time of your execution with the amount of time developing the code, at that moment, there is a big advantage on writing the code in Python. Even if the execution is longer, the time of developing, debugging, and getting the code to do what it's supposed to do is much shorter. Instead, with Fortran, you have to start defining variables. There is a lot of overhead in the coding that is responsible for that efficiency at the end. So declaring the types of variables very explicitly, having good care with loops in the right way, in the right order to optimize the code, eventually introducing some parallelizations, all that takes time for the developer. So the point is add developers time plus compute time, and Python in that balance fits very, very well. So that is the message here. Another thing is the difference between a programmer and a scripter. Python is both a good language for programming, for making really big programs, or for making really small programs that fit a purpose, do something, make some looping or something, and execute a very target purpose. We will be focusing more toward the scripting side rather than the big programming thing. Just because this is an introductory course. So the codes, the examples are meant to be short, self-contained. We will not be digging too much into big structures, modules, creating modules, or testing, continuous integration, all those sort of things. No, we will put this a little bit aside. It's good for you to know that this is possible. It's possible to make really big programs. Or even better, it's possible to integrate portions of Python code with some other portions of Python that is reconverted, for example, into C code that is compiled and executes like C, for example, using Cython. This is something that we will not be mentioned. We will be digging into that. But there is one, I think, chapter 8, if you are interested, chapter 8, I demonstrate one code with, I start with an example, unoptimized, and step by step, I am optimizing and then gain like 100%. It takes like 1% of the original time after optimizations with Cython converting execution. Okay. So again, let's focus on the examples. You will have the time to read the notebook on your own and follow this. So this is the first example. Very simple. This is what I call like the hello world of scientific computing. Small, simple. You capture the main elements of the language. And after you have time, you can see what. So this is the code here. So this is the main code here. So I will be defining a variable. This is how you define variables in Python. I am executing a function here, very explicitly, converting from Fahrenheit to Celsius. And here I am printing a message on the screen. That's all that it is contained here. So in this print, I am introducing the way to write the content of some variables here and here that follow the order of this tuple here. So two variables, and the content of those variables, when this is written in the screen, will be replaced by the content of those variables. You can execute that, and you will see the result. So this is the first code in Python, really simple. Now, you can improve on that, and we will be looking into functions and the particularities of all those things. By instead of having the explicit function here as a continuous set of execution, we can just define functions. A function is something that takes an input and eventually produce an output. I say eventually because not necessarily a function needs to return something. But in this particular case, it does. It's returning another, it receives a value and it returns another value. That's what the function are doing here. And we have two functions. So we have a function that converts from Fahrenheit to Celsius and another function that converts from Celsius to Fahrenheit. The names of those variables are completely irrelevant, so they don't need to be like that. You can replace that with another variable. So what is important is that you should keep consistency between the variable that is in the head of the function, in the definition of the function, and where it is used inside the code. So this is exactly the same. Now, once you have defined the function, yes, you can use this function here and here to produce a result for any value that you enter in the conversion. So here you see I am entering Fahrenheit to Celsius. This function is receiving 80 and is returning the equivalent value of the temperature in Celsius. So that is, let's say, the very minimal, what I call the hello world scientific computer. Very minimal. Now, even before that, you can do simple math. You can try executing arithmetic operations in this Python boxes, in this Jupyter notebook boxes, and they work perfectly fine. No problem with that. There is, for example, here a small code that is testing for prime numbers, and they return the prime numbers in a very inefficient way, but they are doing it. So now let's introduce a comparison about the syntax of Python compared, for example, with another language. In this case, for example, C or okay. And for this example, I will be using the quicksort algorithm that you see here. I will not be entering into the details of the algorithm. The point is that this algorithm takes a list, for example, of values, and by switching back and forth the allocation of those values, at the end of the day, you will have the values properly sorted. That's the purpose of that. So I will be writing the code for the algorithm that is capable of doing the quicksort, an implementation of the quicksort algorithm in Python, and compare that with the same, pretty much the same algorithm in the structure, in the working, in another language, C, for example. So this is the code written in Python. And here you see the code. Let me see if it fits. It doesn't fit exactly, but it starts here. It starts here, written in C. It's doing exactly the same thing, but notice that here, a lot of those things, loops, that here are expressed as for loops. So things that are iterating can be replaced with just one line, which is basically doing the same. So there are some compactness in the way you can program in this language. They both do the same thing. In this case, if you compile this, there is some advantage on executing, tiny, but still there isn't a small advantage of executing in C. But you see, the code is not so small. And another thing, in this case, if you want to run this, you need to take the code, put it in a file, compile the code, and execute. There are some extra burden on doing that. Instead, in the Python side, you just type this. It's a definition, and you can use it directly. So the compilation and all those things is hidden behind how you convert this text into an executable programming code is hidden. While in C, in Fortran, is far more explicit how you do it. And you need to define if a variable is an integer or a floating point number or whatever. So you need to be very, very explicit on those definitions. Okay, so that gives you an idea why Python allow you to write really, really compact code that are still understandable. It's not that I'm making a super esoteric code. Once we learn about these list comprehensions, you will see that it's natural. It's doing a loop, but in one line. Now, let's move here. I mentioned that it's now less relevant now. Nobody programs in Python 2 anymore. So anyway. So now let's move to another example. And it's this one. Again, using functions. This is a fractal that is the product of an function iteration. So we have 4 functions here. If you want, those are matrix vector multiplications plus some translation, and depending on some weights for some probability factors. So you start injecting the pairs of numbers and you get another pair of number. And when you plot those points on the screen, you are able to create a figure that we will see in a minute. So you see, all those are probabilities. They sum 100 or from 0 to 1. So depending on the value, you start from 0. The idea is that you start from 0, 0, 0. So you start in the origin, and you select a random number. Depending on the value of that random number, you will be executing this function or this function or this one or this one, depending on those probabilities. If you insert that into the function, you get another point. And that will be the next point that you will be using for the generation. The idea here is to demonstrate how you can write functions that do this. Here, in this case, I am using another library just for efficiency, and that is the NumPy library that allow me to create arrays, multi-dimensional arrays. In this case, small 2 by 2 matrices, because I will be multiplying that. uh, for a vector. So, and here I am doing the dot product matrix vector multiplication, and I will be getting the new values. And here, what I'm doing here is the loop for a certain number of points for all those functions. And if you do that, well, in this case, 100,000 times, you will reproduce a very famous fractal that is the parsley flat fern. So it's like a leaf. So what is important here are a couple of things. First, there are libraries like NumPy, like this library that I'm showing you here, NumPy, that are specialized in the numerical operations. When I'm doing this, for this case, it's kind of overkill, and I could reframe this code. I can put this frame without using NumPy, but I prefer to guide you or show you that there are libraries specialized for mathematical operations, and those fit that definition. And there are libraries specialized in plotting. So I'm using those libraries. Matplotlib is the de facto standard for plotting on Python. And NumPy is the standard for manipulating arrays, matrices, vectors, not only when they are small, but when they are big, and the performance is impacted if you try to do it with lists, with some other structures in Python. And so there are better ways to do that. And you see this, even for 100,000, it takes no time to get the result. So it's really efficient. Now, I will review this a little bit. Variables, you can read it on your own. I will try to skip and going into the examples and trying to see this. So variables, you can define variables like integers, floating point numbers, or decimals. Just defining it. You don't need to a pre-definition of a variable of being of a certain type in Python, and you can change that. So they have an internal type that is kind of flexible, and you can change those on the fly. So there are a few basic types. The usual mathematical operations were with them. The order of the operations is also important. Strings. So there is some, okay, there is some nuances here. You can define what we call strings, which are words, strings of characters. And there is a way, let me see, how you address specific positions of a string. In Python, the positions start from 0. So this one is the first position here. So if you have this word, M is in the position number 0. You can define like ranges of strings. So, and there are several ways of doing that. You can start from backwards and say this is from position 12 to -7 for this, or from 0 to 5. And it will take all those elements from the first 5 characters. So you can try this and check what is happening there. What else? There are several ways, and this is important because if you find a code that doesn't run on Python, it looks like a Python code, but it's not. Sometimes it's because it's a Python 2 code, and you notice that immediately because you will see something like this. Print used to be just a statement, and what you want to print, you didn't need to put a parenthesis. That had changed. And this is one of the big changes between Python 2 and Python 3. So that's why I'm highlighted here, the fact that in Python 3, the newer version of Python, you need to explicitly add the parentheses for the printing function. Print is now a function, and you need to put it the parentheses in place. When you print, remember the first example, I was printing the numbers from Celsius, Fahrenheit, all that. There are some string formatting that you can use. As for strings, I was putting something like this for an floating point number, a decimal number. There are some formats here for scientific notation of numbers or integers. So this is something that you should learn how to print those numbers in the proper way. Let me see, let's try to go to the next example. Oh, there is a new way of writing strings that emerged in Python 3.6, and many programs now implement that way of printing the styles for formatting strings. So it's very likely that a code that has been developed recently, it will not work on Python 3.5 or something. So there is there is an important jump between Python 3.6 and 3. But over time, it has been getting older and older, the Python 3.6. So if you connect to a cluster, if you install Python on a computer, most likely you will have 3.9, 3.10. So you should not concern too much about that. But I wrote this notebook back in 2020. So at that moment, it was kind of a time with Python 3.5 was around, and certain ways of formatting were still not available if you try to use older versions of Python. So that's the first thing. So variables. Check the examples, try to change your examples. So what I suggest there, if you search over internet, for example, for the front, this is the original parameters for the, what is that? But you will see that there are variations of this, of this form. So with different parameters. So for these functions here, if you change the numbers, you get the leaves twisted in one direction or another, or the figure is distorted somehow. So you can try to fill those and get an idea and play a little bit with that. Increase or decrease the number of iterations to feel what is happening with the points. And with that, little by little, that will give you familiarity with the language. So again, you learn a programming language by touching the code, not by reading the book. It will not help you as much as touching the real thing. So let's move on. Let's see. Okay. Now let's go to the next section, which are the loops and conditionals. First chunk of the language is knowing that you can store data with variables. The next portion of the language, the next thing that you need to learn is how you organize those variables into bigger structures. One, and how you can redirect the execution while you need to repeat an execution over and over, or you need to decide diverge the execution into different paths based on some conditions, on the evaluation of some operation. So the first thing is some mapping types. One very common type is our lists. You can define lists with the square brackets explicitly, like this. You don't need to use a specific type. You don't need to be consistent with the type on a list. And there are several ways to capture values from the list, or slicing, so cutting the list from one place to another. That is called slicing. All those things you can do with lists, or you can iterate over lists, all that. What is important to know here is the lists, even if they are part of the language, in scientific computing, you should try to avoid them as much as possible. Because in real numerical computing, you will, if you are facing a point where you need something like a list, you should see if it's better to create a NumPy array. It will be far more efficient. The operations with NumPy arrays are taking place with a lower level, some coding in a lower level language. So try to avoid lists as much as possible. For small things, yes, you can use lists. For a few tens or maybe 100 elements and you don't pay too much attention, yeah, you can use lists. You can have lists inside lists and they will be something like a matrix. You can do things like that. But at some point, there is a huge penalty trying to use lists as your tool for arranging elements in sequences in a list. So be careful with that. Oh, what happened? Huh? Something happened with my tab. So I'm reloading my note. Questions. If you have questions, that this is a good moment to stop. And I have like 7 or 8 examples, and I will start jumping into the examples, showing a little bit how they work, and allow you to follow the material on your own. Let me see if I can jump quickly here into the section number 2 here. Okay. So I was talking about the slicing. I was talking about trying not to use lists as your primary way of storing vectors. Especially vectors and matrices are central to your execution. Don't try to do that with lists. Lists are very easy to type and all that, but they are really not efficient for numerical purposes. So what else is here? And you can add, for example, lists inside lists or things like that. So here it's explaining what the deep copy means. So you want to copy the elements to make copies of lists. Otherwise, what you are doing is like a reference to the same list. If you change the first, I think I have something like this. Yes, so I have like a shallow copy. You have a list. You think that you are doing a copy of the list, but if you change one element of the list, you are changing the original too. So here I'm making the case for making the distinction, which is if you are a beginner in some languages, in programming languages, you could be thinking that you are making a copy of a variable when you are just doing another reference from the same positions in memory. So that's why I'm showing an example of shallow copying and deep copy. Okay, But let's move on because the time is short. List comprehensions. We use this kind of thing in the quick sort. You notice the quick sort was like 10 lines, less than that. The reason why it was so short is because all those loops that were very explicitly written in the C code were replaced for things like this. This is another way, or I don't know what it's doing this. It's somehow erasing that. So things like this. So it's compacting a loop cycle of things in just one line. That looks like a prescription for creating a list on a certain number of values. Okay, those are lists. This is one way of storing data in Python. It's in the language, it's part of the syntax, the list. Another way of storing data are dictionaries. Dictionaries are mappings between some keys and some values. The keys could be strings, could be numbers, could be many things. And in this case, I have strings as the keys. Another way of storing data here. Oh, this code is doing something here with my box. And I don't know what it's doing. Okay. It's erasing it. Okay. So with dictionaries, you can store, for example, the certain characteristics of an element that you can use later and address some data. For example, you have the periodic table, you have one element. For each element, you have the name and you have different characteristics for that element. So you can use dictionaries to pick up the values that you want, the different properties of an element, things like that. I was showing here the example of the Platonic volumes right here, and how you can pick the number of faces for the name of the element. So that is, let me see if I can, and sets, this is another way of storing data. It's a little bit more efficient than list, but you cannot change the number of elements there. So, and you cannot have repetitions. So all of them are different. How you loop on them, and tuples. So tuples are really static. You will not be able to change those. If you decide that those are 3 elements, if you want 4 elements, you need to create a new tuple because you cannot enlarge the tuple. While at least you can enlarge. You can append elements, and it's described there how you can append elements to a tuple, to a list, sorry, but you cannot do that with a tuple. So lists, dictionaries, sequences, and tuples. Now, once you know how you have those ways of storing multiple variables in one single entity, like lists, like dictionaries, the next thing that you need to learn are conditionals. So how you bifurcate the executions based on a certain expression. So here are the basic operators for comparing values between numbers. There are some others for comparing strings. All that is here. Conditionals, so how you separate the execution. If something is happening, you do this. Otherwise, you will be doing that. I have a few examples with that, so I will go into the examples for that. And I will give you some time for the exercises here. So see there, we have the conditionals and the loops. I think the loops are here, the loops. So how you repeat executions over and over. Before that, you need this range, for example, to create an iterable, something that you can iterate over and over for repeating the execute. This is just one way of doing it. So now let's move to functions. And for that, I have another example here where I am defining a couple of functions. So what I'm doing is another factor. This is more visually appealing, I think, where I'm defining a couple of functions. And I'm using complex numbers. Notice that from the very beginning, when I define variables, you have integer, you have floating point numbers, like real numbers, decimals, but also Python has integrated complex numbers as a variable, so you can work with them. It's part of the standard library, so a big pool of libraries that is a standard and you can expect to have no matter what is there. So I will be having this function which take a complex number, a couple of complex numbers actually, but one is a constant and another is a value that I plan to change over and over, and return a constant, another complex number. So this is my function here. It will be a square the complex number, adding the constant c, and I will return some. And for this function here, I will be defining how many times I will be iterating the mapping. So this is very similar to the firm. Again, we are iterating, and the idea is to see if a certain point, you start from a certain location, and you will be following this prescription for a certain C. You will be following the prescription until this point escapes. This point goes to infinite at some point. So that's what I'm doing here. And you decide a threshold here, here. So you can demonstrate if the value reaches a certain radius, there is no hope for that point. The point will escape. So that's why there is a threshold here where you iterate many times. As soon as you reach the threshold, the boundary, this point will never return, will never come back. So that is the point that is out of the set because it's iterating to infinity. So that's what I'm doing here. I'm iterating. You will have time to review and looking over internet what the function is. What really matters here is that I'm defining a couple of functions. Notice that in this case, I am returning something. This is a function that looks like a mathematical function. This is something that is taking some input and is returning some. Here, I'm not returning anything. Well, like here, I'm returning this. Well, yes. But what I would like to do actually is use the matplotlib functionality to take all that, the matrix that is created, the figure that is created as a byproduct of this operation, make multiple times, many times for that, for all the values there, and just put the image on the screen. And that is the function. And if you like, and this is something that is helpful for scientific purposes, one of the things that you can do, for example, is for a case of research or something that you are creating a plot. Once you have a plot, you can export that figure, the image, into a PNG file that later can go into a paper, or a PDF file that also can go into, depending on which structure are you planning to publish your paper. A PDF is very good for vector images, so for lines or things like that. PNG files, JPEG files are better for something like photos or things where you have many colors and the idea of vectors is not so clear. So in this case, for example, a PNG files fits the purpose really nicely. You want to put that in the paper, you can create a figure, export the figure as a PNG file. You will get, at the end of the day, a PNG file alongside your Jupyter notebook, and you can use that, transfer that to your own computer, and there using LaTeX, or if you write your paper with Microsoft Word or something, you can integrate that figure into your paper. But keep in mind that this is like an approach processing tool. You have your input, you create the plots, and the plots are aggregated into your folder here to be used later for publication. That's what I'm doing. And this is attached to one of the challenges that I will demonstrate. This is, well, I will show the two fractals. You can pick one of those for a challenge that I have for you in a minute. This is another fractal. It's like complementary to the Julia set. They have a relationship between Julia sets and the Mandelbrot set. In this case, I have again a function that is returning a number. Under some circumstances, it will return not a number, so the value is k here. And I start from a certain position here. I do the iteration. I am saving the figure. In this case, I'm saving the figure as a SVG file, which is a vector file. So SVG files, PDFs, PostScripts, all those are vector images. So those are the formats that you should use when you are thinking about vectors, lines. You're describing, you are computing something, an experimental result with some post-processing, but those looks like lines of some sort. A vector file format is better. If this looks like an image, like a photo, try to select PNG files or JPEG. The difference between those PNG files, JPEG work better if you have nuances of many colors. You have gradients of colors. The algorithm is very, very efficient to manage that, like a photo. While PNG files are much better when the number of colors is fixed and is reduced, and you have a good contrast between the different colors. So PNG probably is the best for this kind of figure. But still, I put the file as a vector format to keep it here. Now, this is the challenge that I will be demonstrating for Friday. You can get different Julia sets depending on the value that you select for C. You see this C value here. This is the traditional value. This is, let's say, one value. But depending, if you change C, you will get a slightly different, distorted, another Julia set for a different C. Now, if you start following the material and learning a bit about how to program this, you can take this code and try to do this, recreate the plots, so many plots for different values of C that follow a line. So you decide a line with a certain slope, and probably starting on this point, and with a certain slope, you will be creating a set of points. And the idea is to create, for example, 1,000 images of this that will be slowly changing the shape as you move the values of C on a certain direction. And Friday, I will show you how you can integrate those figures, so 1,000 figures that could be PNG files or JPEG files, to create a video, which is another cool thing to know, to learn in different research domains. When you have, for example, the results of experiments that have been carried under many different circumstances, and you have figures for them, and you want, for example, for a presentation, live presentation, to have like a video that shows the difference between those things. So I will be demonstrating how you build videos from a collection of figures. But for that, I have this challenge for you to start with a certain point. That could be this point, decide that as a slope. You follow that very tiny steps, really, really tiny steps, like 1,000 steps along the line. And every single time you will create a different figure, and you will export the figure with number 1, number 2, with that certain suffix, different numbers of those figures. And later I will show you a command on the terminal that you can use to build an MP4 video out of those collections of images. Okay. Now, here I demonstrate a couple of functions, really small. Python itself, they have some functions, like those, for example, for converting an integer into a floating point number, or certain value into an integer. There are a few that are built in with the system. And the important is you should know this the name of those. Because if you try to create another function with the same name, your function will take precedence over the internal function. So you can create a big mess if you try not to use those. Select a different name. So that's why it's important to know which functions are built in to avoid them somehow. Okay. There are more things in the standard library. The standard library has, as I told you, many functionalities, many modules, functions that are standard. You can count on them no matter what. Any Python installation will have those functions. For example, the math library here, the math module here, you can use it, for example, for doing simple calculations, logarithms, square roots, things like that. Factorials. There is, for example, another module here, the calendar. If you want to print a nice calendar for a certain month, you can do that. And you can. So there are many libraries there in this notebook, but I don't think that I will have time for. I will give you this for you. I will not be covering the standard library. So I will try for the next session to focus more on the Jupyter and on the NumPy pandas. I really want to show you that NumPy pandas and some things related with the scripting. So focusing more on how you can use Python to automatize certain executions. So let's move on to another. Okay, so now I have another example here. Let me see here. I'm missing the. Here is supposed to have a, and I don't know what is going on. The Fibonacci sequence. If you don't know that, search for that or internet. There is a prescription for create a sequence of numbers. You start from 1, the next one is 1. So you add those two numbers and you get 2. Now you add the previous two numbers, you get 3. Now you get the next number will be 2 plus 3, 5. And you will continue to follow that prescription, taking the previous two numbers to create, let me see if I get that, something like this. The idea why I'm using this is just to demonstrate that there are ways of calling functions that call themselves. So there is here. This is a function that internally is calling itself to create the sequence. Another, and eventually the lambda functions, which are small functions that are so small, so simple, that they doesn't deserve even a name. So just the mechanism to operate with them. And they are very, very commonly used in Python. Lambda functions, they are here. And I think I described those in some other place. So the fact that you can iterate on functions and the use of lambda functions to make the code short. So all those things make this Python language very, very compact. And here I have the Fibonacci sequence extended to very large, well, to some large numbers. And I hear this is not Python. This is the notebook that allow me to test the efficiency of a certain piece of code. So I am testing here how good it is to use an alternative way of writing the function compared with the traditional way. So this one, for example, this is the notebook that allow me to do this timing. It's actually executing the function multiple times, taking an average, a standard deviation. They will give me some statistics. So I have one way of executing this. The free one, so actually 3 ways. Let's see. Well, at least here I have a timing here. What I'm testing this, for this one, it takes 17 microseconds. And here I have another version of that is taking a little bit less than that. So those are things that are, if we reach the Python thing, I have something like that. So where you try to beat with better and better algorithms for certain critical parts of the code, and try to reach the most performant version of that. Let me see what, okay, I'm doing all that. And okay, and I'm describing what's going on and the relation of the Fibonacci sequence with the golden ratio. Okay, I will skip in that. Another thing that is important in Python, some people use it, are the functional programming. So when you can imagine functions that operate on, let me see, let me see for a good example here. Well, a lambda function is like a mapping. Yeah, let's keep it like that. I will go quickly on the object-oriented programming because I put most of the effort on the scripting side, and the object-oriented programming is mostly used when you are dealing with big programs. I will give you the idea, or the basic idea here. Object-oriented programming, first, Python, you can program in Python under different models or different structures. You see programs that have functions, so that is a structured programming. You can use Python with functional programming when you have maps and iterate with them. That's one way. Another way is to have objects, classes, which are often used when you have big programs and the idea of an object, which is an aggregate of some variables and some methods that work together like an entity, and from then you can iterate, you can operate with those, with instances of those classes. Fits a natural way of programming. C++ is a very typical example where the object-oriented programming is heavily used. And in Python, you don't need to use object-oriented programming, but it's there, it's available. And the idea here is to define what is called a class. The class is like a recipe for an object. An object is an instance of a certain class. And you define specific function, very special functions that receive names. And this, for example, here, the init, is a special function that is called every single time that you want to create a new instance of a certain class. And those objects, so the instance of classes, could have methods, so functions that naturally operate with the variables, internal variables of that class. So here I have a very compact example. I have another example here, but I would like to move you into one particular example in mathematics. Again, unfortunately, I'm missing some of the math here that should be appearing.
It appears in mine.
Yes, sorry?
Yeah, I can see the numbers in mine.
Yes, probably did something, probably with the version of Python that I'm using, and probably I should have used a different, something is missing on my side. Or if I could, I will try that at some point. I will try it and will give you some time, and I will try another version of Python where I know that I have the machinery that allow me to put these equations in place. So the idea is you have natural numbers, you have integer, you have rational numbers. And rational numbers are a subset of the real numbers, and the real numbers are a subset of the complex numbers. And beyond complex numbers, there are some other entities, and quaternions are just one of those. They are widely used in practical applications. So they are not just mathematical monsters or things like that. They are commonly used, for example, to operate with rotations, to guide missiles, or to compute positions and doing rotations for games, for example. They have their own use. They have practical uses for those. And what is important for them, in the meantime, I will be trying to open another notebook. And this time I will be using something, maybe this, maybe one of those. Okay, I will try to use that in a minute. Because I would like to see this. I will see if I can get it. So the important thing about quaternions is that they follow a prescription for the multiplication table. You know, for the complex numbers, there is also a multiplication table. If you are having an imaginary number times a real number, you get an imaginary number. So 1 times I, you get I times 1, you get I, but I times I, you get -1. So you can build a table for the multiplication of complex numbers. You can do something like that for quaternions. The multiplication number is 4 times 4. And beyond quaternions, there are octonions, septennions, there are other mathematical entities that they serve their purpose. Those are nice things. They have very nice qualities that emerge from them, and they are not present in those lower level cousins like complex numbers or complex numbers, real numbers. For example, commutativity. Some of those things start been lost when you scale in those other systems, in those other fields. Okay, let me see if I can get this. We'll try to open another notebook here. So what I would like to do is to use the ideas of object-oriented programming to deal with quaternions. So, and here is the code. So again, this is for me an excuse. I would like to use quaternions as an excuse to show you how I can create another class that is called quaternion, and operations, the operations that I do with the quaternions are integrated naturally into the structure of the object, into the methods that I have for that object. So I have the initialization, the constructor here. This special function is called the constructor. Let me see if I can get into the. I will see how you do, how you create the unit elements of the quaternion here. So the real number in quaternion form, or the complex number in quaternion form, or the other elements for the quaternions, the first entity, how you add. So you can define a function, a method that takes one quaternion and adds another quaternion and returns another element. All those things are here. And what is important to know is that operating with quaternions, once you have defined that object, became very natural. It's easier to work with them once you have defined those elements properly. So for example, you can have a quaternion defined a certain way, and you can check if two quaternions are equal. You can do operations with them. Let me see here. So you have two quaternions, you can add them. You can do all the operations by creating those classes there. So that is the main purpose of this. So all that is here. Let me see if I got that. Here. Let me see. Oh, no, okay, I will work with this. So this is the idea. I have here the natural numbers, what they are, and here I have the multiplication table. So this is the multiplication table for the complex numbers, and this is the multiplication table for the quaternions. So what happens if I multiply this element by this element, you get this. And with this, you can operate with them. You can follow them. And here is the code that will integrate all the operations for the quaternions in a natural way. So addition will look like an addition. Multiplication will do what is expected for the quaternion. All that in an object-oriented way. That's what I'm doing here. So you can follow this. And there are some other things that you can do with classes. There are special classes that probably are going beyond this. But I described them there, but I will probably not go into much detail about them. Like static methods and class methods. So all those things serve a purpose in the object-oriented world. The inheritance is another thing that is important. So you can create objects that go narrow and narrow and have some specialities for them. So let me see. Well, I have another example here. for figures with some sphere or something. And I was returning here back into the temperature exam. But this time I have a class where I can receive a value and convert internally, keep that value in a specific unit, and I can return the value in a different unit on demand. So those are handy things. For example, if you are working on experiments and you want to keep a consistency on the units, sometimes it's not so easy because in the experimental domain, people use some units, but people in the theoretical side use the different units. There are more natural atomic units instead of the international system. So you want to have a way of keeping the sanity of all that, and you can encapsulate all those things into classes that allow you to convert back and forth on demand between the different units. So that's what I'm trying to present here. And here I'm showing a little bit for another class, another example, let's say, for Platonic solids, how you can ask for the properties of the Platonic solids. For example, the number of faces, the number of vertex, properties of the solids, just by asking the class to return values for them. This is another thing. So here I am getting, for example, vertices, edges, faces, and some other numbers, and that mathematicians are interested in capturing, and they have very well-defined functions to return those. And finally, I have here, let me see, this is less and less important, well, I would say, the difference between Python 2 and Python 3, that you should be aware, probably less now in 2024, that used to be when I first wrote this notebook. The first thing is the print. I told you, print now uses a parenthesis. It's a function. While in Python 2, the old Python that nobody uses or should be using anymore, print was a statement. So you put print and you follow by what you want to print without parentheses. That had changed. And now you need to use a parenthesis. Integer division, this is another important thing. In Python 2, if you divide two integers, you get the integer approximation of that. While Python 3 is taking the integers, and if the division returns a decimal number, it will return the decimal number. And there are some extra functionalities if you put the double slash, if you want to reproduce what it used to be the integer division. You have to put the double slash. If you put 3/2, you will get 1.5. You will get the decimal number. But if you want to reproduce the old behavior of Python 2, you need to put a double slash to get 3 divided by 2 equal to 1, to an integer. Another, those are the major difference between Python 2 or 3. The way you create those ranges that, for example, are used in loops, in for loops, you have the old range that used to create a list. Now it creates an iterator. It's kind of obscure. I will not go into much detail, but it's different. Those are different things. And for some purposes, it doesn't matter too much, but it's important to keep those in mind, that there are some difference, and nobody today, 2024, should be using Python 2 format. No. Now, finally, to complete this, and after I will show you a little bit the standard library, but I will not be dealing with that. and I will be presenting completely different things on Friday for the Python section. I offer here, which is encompasses a lot of the what we learned from the Python here with this code, with this. Here, what we are doing is to reproduce a very famous algorithm that is called the life game. So the idea is that you have like imagine like a big chessboard. The boxes on the chessboard, and let's say imagine 200 times 200, something relatively big, and the squares into that board could be either alive, let's say black, or death, nothing, which is white. So yeah, and based on the neighbors of those boxes, of those squares, you will decide on the next iteration if the box will be alive or will be dead, not empty. And you use those prescriptions here. Again, I will not go into, you can search for that from the game live, Conway's game live. So you have the matrix, you put randomly a few boxes there, and you start iterating with them. The nice thing of those, and in this case, for making really standard, I'm not making the animation. There are ways for animating this out of the Jupyter Notebook, which is really nice because you will see some structures of boxes that start moving organically across the board. So they behave like bacteria, and they eat or some other of the boxes, and you will see some growing, some of them disappear. And it's a very nice algorithm, I think from the 80s or 80s, or I think 80s or 70s, not really sure. So that's the idea. Based on the neighbors, and you start with a certain structure, and this is a big picture. So the idea, if you want to see those tiny little animals moving across the board, try to make it something like 200, something like that. You start with a certain population, so a certain population of black boxes or purple boxes in this case, and you allow them to evolve. You allow them evolve multiple iterations, and if you see the animation, you will see there are a few species, kind of a prototypical elements that start moving across the board. And here I am just showing you some of the figures, the sequence of figures that you get when you do that. So the idea here is, again, either the version that is animating this, or for a bigger board, again, this is a very small board, but if you change the size of this, instead of 10 by 10, something like 200, 200. Let me see if I can do it here. I will be getting, and you decide a different density for the initial conditions. So there is also a critical value. If the density is too low, everything dies. If the density is too high, I think that also dies. It oversaturates and dies quickly. So there is an optimal value, and some patterns start emerging on that. The idea is to, again, generate many figures. This is an alternative, and I will show you how you can recreate a video from those figures. Well, it will probably take some time to do that. So I will be moving quickly to show you, because I will not be dealing with this, for you to follow. A little bit about the standard library. You can do this on your own. What I'm doing here is I am picking what I think are the modules in the standard library. The standard library is big. They have many things for network, for all sorts of things. But in real scientific computation, most of the time you are working with the same stuff. So I am selecting like 10 modules here, and I am developing what I think people could use in scientific computing. So the SIS, of course, this is very central. The math, the EOS, and if you are trying to create folders, go into the folders and recreating some files, and you use the OS, you use the SHUTL, iterations, iter tools. If you are storing data, the JSON module is important. And there are a few here at the end that are important when you are dealing with parallelization. And as this is for a high performance computing, so let's try to show you a little bit this one, and I let you read everything else. So we are operating this on a machine that has 40 cores. I asked for 8 or 4, I think. So I have 8 cores for me to work. And sometimes the kind of things that I'm doing, even in Python, are kind of computationally intense. And there are natural ways to parallelize those. As soon as the values in the are sit on the look into the same memory on the machine, I could, instead of asking for 8 cores, I could be asking for the 40 cores of the machine, and I could divide and conquer. If I can do that, if I can think about my problem and split my problem in small sections that deal with a specific portion of the data, and having others that are doing pretty much the same on different portions of the data, and after I'm collecting the partial results, those kind of problems, those kind of situations are naturally for me to convert into a using the multiprocessing model. So, and notice we have 40 CPU cores on a machine like this. Probably on your own machine, you have 4 8 cores. So this could be handy. How that works is really, really simple. You just need to import the multiprocessing module. You have, for example, here a function. You define a function here like this, where you are doing something repeatedly, like this here. And you can ask Python to process that function for batches of inputs separately on different cores. So with that, ideally, you can cut the execution time by the number of cores that you have on your system. For example, let me see one example here. Well, here I have on a separate script inside this folder scripts, which is, let me see, it's around here, scripts. I have a worker. Let me see if I can look into this code. Yeah, so I have a few functions here. I would like to use some of them. Probably it's one of those. To remember which one exactly. The point is that I have my functions in a collection, a separate collection. So, and I would like to operate with all the elements, for example, on a list, on an array. I have 1 million elements, and I have 4 cores to work with that. So I can cut those million elements in chunks of 250,000 and ask this pool to process the function that I would like to process for those 250,000 on separate cores. That's what I'm doing. I'm here. Okay. When I run this, because I'm not executing this, I was using a machine with 52 cores. And at that moment, then the pool size is the number of cores on the machine. So I will be processing that, and I will probably taking some time in. Okay. So this is one of the things that you can use when when you are working with big problems. So some people ask me about this example. You can see this here, and let me see if we can go back here. And this is a quick overview of some of the Python packages that I will be dedicating for the next session for Friday. So here, scientific packages often used are NumPy. This is something that definitely I will be dealing with on Friday. SciPy there are a few examples here. So those are libraries for dealing, for example, for the special functions, Bessel function, spherical functions, those sort of things. Spatial decompositions, Voronoi decompositions, so the fast Fourier transforms. So scientific operations that are a little bit more elaborated are there in the SciPy. The matplotlib, I show you a little bit the plotting capabilities, matplotlib. There is a subset, or there is like a child of matplotlib that is specialized for machine learning or data mining or data analysis, which is Seaborn, that allow you to do some of the typical figures that you do when you are in that area. So matplotlib plus Seaborn, symbolic math. Some people use that, and pandas. So for the next session, I will be concentrated on those two, especially NumPy and pandas, data analysis. So I will show you some example of that. If you just want a quick overview of those, here I am showing a quick examples of what this is all about NumPy, the idea of arrays. This is something that I will go deeply into, how you cut arrays, you slice them, how you manipulate arrays very, very efficiently in Python. The SciPy, here I am showing you what's one special function, for example, the Bessel function, and I am probably doing the plot here, something like this. This is like a ripples, so I'm taking something that I create with the Bessel function, and I'm just plotting that here using matplotlib. So this is matplotlib, or the ripples in a 3D figure are right here. Symbolic manipulations, so solving some equations, algebra, eventually with some derivatives is over there, and pandas. Probably pandas is more important, so for most people, and NumPy. So I will be focusing mostly on pandas and NumPy for the next session. And here in this particular case, I am taking, for example, an Excel file for statistical indicators of the welfare of nations. And I'm trying to manipulate those. This is relatively old, so this is pre-COVID, 2018. I will try to get a newer version of that. So where you can analyze, I think that you have some figures here, the behaviors of some variables like schooling statistics for I think a couple of countries, I think, and that I select, or for one country across multiple years. So those things are the natural, pandas is the natural to deal with data sets, tables of data. So I will be devoting some time to explain you a little bit about that. Questions, we have 4 minutes for questions. If you have questions, if you had some comments, again, feel free to use this. The reason this was not working fine for me, so if you want to do this with the equations. Either you use your computer and the machinery for making the equations of that. Otherwise, try to use one of those official Jupyter images which have more packages included compared to the Python that I was using initially. And I was skipping some of the equations and some of the math formats inside. But other than that, they will operate the same. They are very recent. Okay. And I think, let's see. Yeah, I will be working with NumPy, pandas, and I will not have time for Panda, for Cython or parallel computing on Python. This is out of scope for this shorter version of the mini workshop. Next time will be pandas, NumPy plus pandas. And a few examples of manipulating files, so creating folders and automatizing some executions. And as I told you, if you do for the Julia set, I will be doing my own version of that, and I will show you how to animate that with some commands on Linux. So that's the purpose of that. Any other question, comments? Feel free. I have a couple of minutes to entertain a few questions. Otherwise, Friday will be continuing with Python, or Friday during the morning, I will be showing more things about how you execute, how you get software from the cluster, scientific software, and how you execute the first jobs on the cluster. So that for the main workshop. Otherwise, for Python, it will be Friday afternoon. And the sessions will be uploaded on YouTube, hopefully today. Otherwise, maybe tomorrow or something. We will have those. The raw videos, at least.
Dr. Guillermo,
Yes.
When we apply the resource from the Jupyter Notebook, so you need, because I tried to use 4 cores, so but it didn't succeed. So you need how to apply the resource from this Jupyter book, and then how to, because when I log into the Jupyter book, it will direct me to the my username, but not the Scratch folder. So how to change it to that folder?
Okay, so your question was related to how to access the Scratch folder?
Yeah, and then how to you need how to request the resource from the Jupyter book, because it's very difficult for me to get the resource.
Okay, now, well, okay. Let's clarify a little bit that.
Two questions. Yeah, thank you.
Okay, so you request the resources before you create the Jupyter Notebook, right here. So, for example, here, if here you select this, and here is where you select the partition that you want to use. In this case, standby, and the number of CPU cores. So if you like to use a whole machine, you request the 40 cores.
Okay.
And let's say 4 hours. Let's try to see if I can get this no GPU cards, Jupyter Lab, and this is turning. So I will be selecting this, for example, standby, 4 hours, 40 cores, an entire machine, and Jupyter Lab. I launch that, and we'll see, and something that I can do is to kill some of those I will be deleting some of the notebooks here.
Yeah.
And delete here, so I will get. Oh. This one. So here I'm requesting one machine, 40 cores. So the request for resources come before you open the notebook. When you open the notebook, you already have access to all those cores. What I will be doing is demonstrating the multiprocessing thing. So you see the jobs that are there, and that the system is able to see the 40 cores. So several ways of looking into this. So one is that, for example, if you open a terminal inside the Jupyter Notebook, one thing that you know is, for example, you can see the environment is learn, and you will see all the variables related to Slurm. So it's Slurm who will assign a certain number of resources for this job. This is an interactive job. This is one of your jobs. And here you will see the the CPU on node. So you have access to the 40 cores on a machine, on one machine. Better still, here you have non-procs and procs 40. You can use the 40 cores. You will be able to see all those 40 cores. And that's one thing. Now, if I close this one, for example, and I go here, for the standard line, and I move here to this.
Yeah.
If I execute this here, and I ask, how many cores do I have at this point? It will tell you 40. So everything that I'm doing, multiprocessing, for example, will use 40 cores. So Python already knows here, at least the multiprocessing module immediately checks that you have 40 cores available for you. And now, yes, you can have something like this. From the worker, I am importing one of the functions, the function that computes the square, x squared, so one of the simple functions. Here I have a pool. As I'm not defining the size of the pool will be the total number of cores that I have on the system. So all the 40, I will be using all the 40 cores. If I am this function, imagine that this function is trivial. It's just x squared. If you see on the squares, if you see here the worker, this function is one of those. It's a stupid function. It's just computing now x squared. But if it's something complex that takes minutes to compute, okay, and you have thousands of elements to compute that, well, the pool could give you an advantage. You can operate with the pool. You will be looking into all those cores and doing the operations. All those cores will be busy crunching all your process. In this case, it's trivial, so it will take a very short amount of time. So what I'm doing is I'm taking a list of 10 elements here. So create the iterator, created a list and iterating on them to compute the square of all those elements from 0 to 9, the square. And so if I change this one, but still the function is so small that it doesn't do much. So here again, I can force a certain number of processes. Let me see if I can, yeah. So here I only have, even if I have 40, I can force my pool to have only 4 processes. For some reason, I can constrain the execution. Or because I am doing something like some of the cores will be doing some operations and some other cores will be a different kind of operation. So I have different pools, so I could decide not to use those all the 40, but divide those in different workers that we will be doing different things. But again, all the process by default, they are assigned when you request the job, when you request the interactive job. And all doing here, all is happening here. Let me see. Is taking all the cores. And if you see another way of doing the of looking into this is looking into the jobs, the active jobs here. My jobs. You see, I have one job here. And if you see the characteristics of this job, I request 40 cores. This is another way of looking into this. So the number of the resources, in this case, time and processors or cores, is decided in advance. It's decided before you submit the job. And there are some other things that you can do a little bit more advanced. In the Jupyter Notebooks, you can also request multiple machines for working in parallel. I don't know if for this particular version of Python that I'm running at this point, if it's enabled. I don't think so. Yeah, probably not. But there are some of them that has the Python parallel. So in those, you can have multiple machines and the machines. So if 40 is not enough, you can also extend and use more machines for person. Or you can use something like MPI for Pi, so for doing distributed parallel programming. But that's another thing. Again, the statement is the same. The amount of resources is designed from the very beginning for you submit the job. Before you create the job, you need to decide here the resources. So the partition, but more importantly, the number of cores that you want to use for the job. Is that what you ask?
Yeah. Next kind of some simple one is how to switch from the user slash my user number to the scratch folder.
Oh, the scratch folder.
Yeah.
Okay, so the scratch folder. Well, let me see. Maybe I can do it. Let me see if I can do it here.
Oh.
Scratch. This is one way. If you don't have let me see. Oh, okay. Okay, this is something that I need. Let me see. Okay, this is something that, no, but I have it.
You have a scratch, yeah.
It's because I have a symbolic link. So I have a symbolic link on, let me see if that works. No, yes. Okay, I see what is the problem here. Let me see. Yes, I can see my scratch, but my scratch is in the real location of the scratch, which is /gpfs20/scratch/ my username. What is not present is the symbolic link that is in the login node. That's the scratch Franco is not mounted, I think. No, is there? So no, yeah, the scratch is there. I was thinking that it was not, but yeah, there are several ways. For me, the easiest is always to use the to have a symbolic link, it's just because it's easier than start moving here. So this is the idea. When you create the Jupyter Lab entity, it will put you on the home folder. and it will not allow you directly to jump into the root directory. So it will position you into the user Franco in my case. And the easiest way to jump into the Scratch is because I have a symbolic link to jump into my Scratch. But I think I cannot change to this path, for example. No, it will not work. It will not. Yeah. So have a symbolic link. There is probably another way of doing this. But yes, so create a symbolic link. So something like this I will show you.
Okay.
So
then I can just run the code in the home directory. So before
yes, but then sometimes the data is so big that you cannot have it directly on the, so you have to refer to the data on the Scratch. So
yeah. So if there's nobody asking question, you can ask another question.
Sure. Let me see if I have another question here. Well, I see it mounted. Well, we'll see. So it's there. I am inside the Singularity container. So this is because I'm using the Singularity container. So I was wondering if the Scratch was there. So I am using this container, and in fact, I have the Scratch there. So Scratch is there. Anyway, sure, tell me.
Okay, so I try to run some neural network code, but usually they require some package. So usually I try on the solid flat, but then the package will be not enough. So is it possible to customize my own running environment or companion environment, or I have to build that by myself? Kind of use another machine. Is it possible to kind of run the neural network code on?
Okay, I will see if I understood what you mean. Okay.
So it's kind of quite very simple. Is I want using the physical informed neural network code. So they will use the torch package.
PyTorch.
So, but you need a torch package, yeah, PyTorch.
PyTorch. So you want to use PyTorch, and you want a package that is not in this
Yeah.
So this is how you do it. This is how you do it. You open here. You have a here. Let's say, oh, this is that.
So kind of some packages missing. So when I encounter that info,
so
what should I do?
This is the idea. You cannot install packages from your Jupyter notebook because the Jupyter notebook is running on a compute node without internet access. There is no internet access in the Jupyter notebook itself. You cannot go here and download stuff. It will not work. So how you do it? You know that you want to use this particular Singularity image, for example, for PyTorch. So what you do is you click here. You see, you load Singularity. So you are on the login node. So you load Singularity and you get a shell, Singularity shell, share containers, and you see. So for this one in particular, you see all the images that we have. Some of them are old, but you mentioned PyTorch. So if you want to use this PyTorch version, okay, so I will be selecting this one, 24.06, which is the latest version of PyTorch on the NVIDIA collection. So with this, I got a shell. And if you want, you can do something like an IPython, or say, no, you don't need IPython for this. Let me see. you want to install something, and imagine that you are lucky and you can do pip install. So pip install. Do you have a good name for the package that you want to install?
One moment.
Doc, I think it's I don't know if it is. Yeah, for example, I found something. So I am able to install packages that will be on my home folder, but they were created from especially for this. So you see it there, it's installed. So this is what I did. I opened Singularity, I got a shell. So I am doing everything. The installation of the package happens here inside a shell of the container that I would like to use. And now at this point, you just execute the installation as usual. And you will notice that the default place for installing packages is not available because you don't have right permissions there. So it will be installing on your home folder. And it will download the whole thing, the package, it will be installed, and now you have. And so if you know the name of the package, this is how you do it. Later, let's say here.
Yeah, and the package is kind of like a Tor. So like that's the
Do you have the name of the package?
Tor.
Can you type that?
T-O-R-C-H. I have
You-
sent that.
Type that. Okay. So for example, it's what is the name? No, but Torch is part of the PyTorch. Torch is
Oh,
PyTorch. So
okay.
if you are using PyTorch, you should have that. Let me
Okay.
give you an example. So I think I select that Torch. So Torch is part. So let me show you. So Torch is not in the standard in the. So well, let me see. If you was here and you select Singularity, if you select one of those, for example, those that doesn't have Torch, yes, for sure. But if you want to use Torch, you first need to go to Singularity container. And now the Singularity container that you want to use is the container that offers you Torch, this PyTorch. And we'll see if this will give me I'm still waiting for that. And I probably have a small mini exercise on PyTorch where I can open and show you that Torch is there. And if it's not in a specific package, for in this case, for example, this docs package is not, and it was that the case, it was not inside the container, you can install it for you, but you need to do it out of the Jupyter node. You need to do it from the login node here. So let me see if I have
So
the notebook here.
after I install this one in the container, but after I finish this job, is everything gone?
What do you mean?
I mean, so is this singularity container is temporary or kind of I can use it again and again?
I'm not sure that I understood correctly. That the idea is all the code for PyTorch is in a file, it's containerized in a file. So all the operativity of that. The data that is generated, if you are generating data, that data is in your home folder, in your Scratch folder, and that is safe. And that is not lost. It's just the code, just the PyTorch and all the dependencies and all that. That is in a file. It is containerized, so it's isolated from the rest of the system. So here, what I have is one example with PyTorch. I'm running this. I notice that I'm running this Singularity container, and I'm able to import Torch easily. I will see. It takes a little bit. But I was not using a GPU machine, so that's why NVIDIA SMI is not present. I'm not, for this particular example, I'm using the CPU version of that. So it will say no, 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 no for all this. False, because I'm not using, some things are failing because I'm not using a GPU machine. But Torch loads, no problem. It's okay, and I can do all the operations, the linear algebra with Torch. What is happening on CPU? But yes, so the crucial point is, and also now that I'm using this, I can, for example, import this package that I installed. I install the package with this name. Well, probably it's missing something in it. There are some other who probably does an old package. I just picked something, but probably some package that apparently no longer works for this version of Python or this version of, I don't know. But that's the idea. So maybe that's the reason. You just select something like this vanilla kind of Python that doesn't include any deep learning package inside. So
yeah.
Or there are a few here in the Conda environments. Some of them include PyTorch too, but for PyTorch, try to use this one. This is the best. This is the most better optimized. There are a few things here for deep learning. So TensorFlow, a very recent version of TensorFlow, PyTorch, MXNet, which is no longer developed, but still DGL for deep learning with graphs. Paddle, which is a Chinese framework, and all their TensorFlow and all those versions here, and for some other packages, for some other things. So all that is there. Okay.
Yeah. Thank you. Thank you. Yeah.
Okay. Okay. If that's it, if no more questions, see you on Friday.